Welcome to Maths with EJD. In this video, we are talking about Pearson correlation coefficient. Of course, first of all, we'll be talking about correlation analysis first, and then we'll go specifically on Pearson correlation coefficient. And in another video, you'll be seeing Spearman's rank correlation. So let's start out with correlation analysis. What is it about? Correlation analysis. Okay. Correlation analysis is a statistical, statistical method used to evaluate the strength and direction of the linear relationship between two quantitative, or what you can call numeric variables, quantitative variables. So the most commonly used measure of correlation is Pearson, the Pearson correlation coefficient. And it is usually denoted by letter R, and it quantifies the degree of linear association between two variables, X and Y. Yeah, so we go next into Pearson correlation coefficient. But before that, at this point in time, you want to subscribe to this channel if you have not done that already. And you hit the notification bell so you can always get alerted when a new video is released. So let's go for Pearson correlation coefficient, which is the most used measure for correlation, because there's also Spearman's rank correlation, which you're going to see in the next video after this. So the Pearson correlation coefficient ranges from -1 to 1, okay? Such that when R is equal to 1, you have what you call a perfect positive linear correlation. That simply means that as X increases, if you have variables Y and X, as X increases, then Y also increases proportionally. Then we also have R equals -1, which tells us about perfect negative linear correlation. So here, as X increases, Y decreases proportionally. And then we have a case where R equals 0. Here, no linear correlation correlation. So there is no linear relationship between X and Y. So the formula for calculating R is this. Tells us that the Pearson correlation coefficient is N summation X Y minus summation X summation Y divided by square root of N summation X squared minus summation X all squared. So this in a bracket multiplied by N summation Y squared minus summation Y all squared. Okay, so everything under the square root. And then here, N is number of data points. Number of data points. Because that will be in pairs as we expect. Number of data points. And X and Y. So X and Y will be individual values. Individual values. Okay. Allow me to be finicky in this situation. So again, N, like I said, is the number of data points. Number, or let me balance that out and go down. So yeah, N is the number of data points, which will be in pairs, like I said. Then X and Y will be individual values of the two variables. The two variables. Okay. Now let's talk about the interpretation of correlation coefficient. Interpretation of correlation coefficient. So it happens in terms of magnitude and sign, right? First of all, talking about the magnitude, if we have 0.9 less than or equal to the absolute value of the Pearson correlation coefficient, and that is less than 1. So we say we have a very strong correlation. This is very strong correlation. So if it is positive, that'll be very strong positive correlation. If it's negative, that'll be very strong negative correlation. So then you have 0.7 less than or equal to the absolute value of R, less than or equal to now less than 0.9, less than 0.9. So in that case, we have what we call strong correlation. And then we can also have 0.5 less than or equal to the absolute value of R, less than 0.7. So here you're talking about moderate correlation, moderate correlation. And again, we have 0.3 less than or equal to the absolute value of R, less than 0.5. That is clearly a weak one, weak correlation. And then finally, we have 0 less than or equal to the absolute value of R, less than 0.3. That is very weak, or no correlation, or no correlation. That's how that goes in terms of magnitude. Now, what about talking about sign? So when we talk about sign, what happens in that regard? So in terms of sign now, if you have positive R, that's positive Pearson correlation coefficient, that tells us that as X increases, as X increases, Y also increases. So that is some kind of direct relationship, direct correlation. And you can have negative R, negative R. So for negative R, now that says that as X increases, Y decreases. Y decreases. And then we can begin to talk about significance of correlation coefficient, significance of correlation coefficient here to determine if the correlation is statistically significant, because that's also important. You can get a correlation value, but you want to be sure if it is statistically significant. So to determine if the correlation is statistically significant, a hypothesis test is conducted using the p-value. You can also use the test statistic. So you have those options. So the null hypothesis, which is H naught, assumes that there is no correlation, meaning that R is equal to 0, and the alternative will just be the opposite of that. And the alternative hypothesis, if you like, that's H1 or HA, depending on your preference. So that assumes, it assumes that there is a correlation, meaning that R is not equal to 0. So here, if the p-value is less than the significance level, which is usually alpha equals 0.05, then in that case, we reject the null hypothesis, concluding that a significant correlation exists. A significant correlation exists. And then we have the second one, that if the p-value is greater than the significance level, we fail to reject the null hypothesis. We fail to reject the null hypothesis, meaning the observed correlation could be due to chance. Okay, so that's how we test for significance, and we're going to see all of that in action in a moment. So let's talk about examples. So we have example 1. We have example 1, which is a case of, it's not looking pretty. Okay, example 1, which is a case of positive correlation. So consider the following data representing the number of hours studied, which is X, and test scores, which is Y. So here now we have hours studied, that's X, and we have test scores, which is Y. Okay, so we have if you study for 2 hours, you get 50. Study for 3 hours, you get 60. Study for 4 hours, you get 70. Sorry, that's 70 up there. And you study for 5 hours with a score of 80, and study for 6 hours guarantees you 90. So that's what we have. And the question is, can you say that the hours studied and test scores, can we actually say that they correlate? That's our task here. And the way to do that is, uh, so I think the question, like I said, is do X and Y, do X and Y correlate? That's the question. So, of course, the way to find out is to use the formula. R is N summation X, Y minus summation X so multiplied by summation Y all over the square roots of N summation X squared minus summation X all squared in one bracket. Then same thing for Y, N summation Y squared minus summation Y minus summation Y all squared that way. So based on what you have here, it tells you how you can go about what you need, right? You need the product of X and Y. You need X, you need Y, you need your squares. So if you want to do the table for this now, it will be something like this. You have X, that's 2, 3, 4, 5, and 6. Then you have Y, which is 50, 60, 70, 80, and 90. And then, of course, you are going to need X squared. You're going to need you're going to need Y squared. And then you're going to need XY. Okay. From the formula, you know what you need. You need the summation of X. You need the summation of Y. You need the summation of X. So that means you need to multiply X and Y and then sum up. You need the summation of X squared. You need the summation of Y squared, like that. So now this is the kind of thing we have. So X squared, of course, for the X squared, you have, okay, I guess I can color code for emphasis. 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, Y squared is 2500, 3600, 4900 for 70, 80 that's 6400, 90 is 8100. And for the XY, 2 times 50 is 100, 3 times 60 is 180, 4 times 70 is 280, 5 times 80 is 400, 6 times 90 is 540. So those are the things we need. So you can now sum up all those things. Now, summation of X is 2 times 2 plus 3, 5, 5 plus 4, 9, 9 plus 5, 14 plus 6, that's 20. Then you need summation of Y, that is 50 plus 91, 10 plus 71, 80 plus 82, 60 plus 93, 50. And then you need the summation of X squared. What does that give us? 4 plus 9 is 13 plus 16, 29 plus 25, 54. 54 plus 36 is 54 plus 36. That should be 90, I believe, for x, 54 plus 90. 54 plus 90. Yeah, that's plus 36. That's actually 90. Sorry. Then you have summation y squared. If you do all that, you end up getting for summation y squared as 25,500. And lastly, summation xy, summation xy. So if you add up all of this xy thing, you get three, you get one summation xy as 1,500 if you do all that together. Summation xy, 1,500. So summation x is 20, summation y is 350, summation xy is 15, summation x squared is 90, summation y squared is 25,500. Of course, n is the number of data points. That's 1, 2, 3, 4, 5. So n is equal to 5 because we need that for the computation. So you can now say, you can now get r. So r now, which is n summation x, xy, and a summation x, summation y, all over square root of n summation x squared minus summation x all squared this way into n summation y squared and a summation y all squared like that. So you can put the values together. So that's n is 5 for sure. That's 5 times summation of xy is 1,500 minus summation x, that's 20. Summation y is 350. So that is over square root of summation, I mean, that's n 5 times summation of x squared, which is 90, minus summation of x, that's 20, all squared, into 5 again times summation of y squared is 25,500, 25,500 minus summation of y all squared, summation of y squared rather, summation of y, that's 350 all squared. It's 350 all squared. Okay. So R is 5 times 5, 1 5 is 7 5 minus 20 times 350, that's 7,000. Okay. All over square root of, for the first one, 5 times 90 is 450. 20 squared is 400. Then the next one, 5 times 25, 500. 5 times 25, 500 is actually 127,500. Then 350 squared is 12,000. I mean, 122,500 that way. So that R now is 7,500 times 7,000 is 500 up there, divided by square root of 450 minus 400 as 50 times the other one is 1,275 times 1,225, that's 5,000. That's 5,000. Okay. So that R is 500 all over square root of 50 times 5,000, that's 50,000. And 50,000, square root of 50,000. Oh, sorry. That's 250,000 actually. 250,000. That's like 500 times 500. So we have 500 divided by square root of 250,000 is also 500. So R is simply 1. That's perfect correlation. So we can say that since R is equal to 1, there is a perfect positive perfect positive linear relationship between hours studied and test scores. So surely, so the more hours a student studies, the higher their scores tends to be. So that goes. So we can have another example, say example two. Now, in this case, I'll just give you the table and the final result, and I'll expect you to go through the same steps I did and get the necessary results. Okay. So this will be for negative correlation. So for negative correlation, consider the following data representing the number of hours a machine operates before breakdown. That is X, and that's X, right? And the cost of repairs, and the cost of repairs, which is Y. Okay. So now we have operating hours, X, and then we have the repair cost, which is Y. So you want to do exactly the kind of thing I did using the formula, right? So I'll just give the table and all that. So you have 10. So if it works for 10 hours before breaking down, so you spend 500 maybe dollars. If it works for 8 hours, you spend 600. If it works for 6 hours before breaking down, you spend 700. If it works for 4 hours, you spend 800. If it works for 2 hours before breaking down, you spend 900. So this is what exactly you have. So the question is, again, the same question. Are X and Y correlated? That's the question begging for answer. If you do your computation well, if you do your computation well, you're going to get R to be minus 0.316 or something like this. So I leave you to work out the process. Don't forget to apply the formula. That's exactly like what I did previously. Just do the same here to be sure you understand the procedure. So we have this. In this case, since R is approximately minus 0.316, since R is approximately that, then you can say there is a weak, it's actually a weak negative correlation between operating hours, between operating hours and repair costs and repair costs. So as the number of operating hours decreases, the repair costs tend to increase. Okay, so we can actually have example three also, a case of no correlation. Example three. Again, I'll just give the table. I won't go through the process because you can just follow what I did for the first one, but I'll give the final, what the final answer is going to look like. So consider the following data on the number of books read per month, which is X, and the weight being Y. So now we have books read. So this is more like probably the books read by someone, that's X, and the person's weight. I mean, what's the connection between the books a person reads and the person's weight? Probably nothing, I don't know. So most likely no connection. So two books, the person weighs 70 kg. Five books, the person weighs 68. Three books, 72. Four books, person weighs 71. And lastly, you have one book, person weighs 69 kg or so. Uh, so that's what you have. So the question is, are X and Y correlated? That's a question again. So, like I said, I'm not going to go through the steps again. Just use the formula and get everything. So here you're going to see that R is undefined because you're going to find that there's a square root of a negative number. So it's undefined. Once you cannot define it, in that case, you have to conclude that R, since R cannot, since R cannot be calculated, since R cannot be calculated due to due to due to the undefined nature of the calculation, undefined nature of the calculation. Once you have a square root of negative, that's impossible, right? Nature of the calculation. That actually indicates that is indicative of a lack of relationship. So we conclude there is no correlation between the number of books read and weight. Maybe as expected, right? So, I think I like to quickly talk about the significance tests. Let's quickly make mention of that. Yes. Um, let's talk about hypothesis testing for significance. Hypothesis testing for significance. Okay. So in the test for in the test for significance of the correlation of the correlation coefficient, we use the t-test. We use the t-test. Okay. We use the t-test. T-test. And it is given us t equals r square root of n minus 2 over square root of 1 minus r squared, where n is the sample size and r is the correlation coefficient. And then we compare the calculated t value against critical values from the t distribution table to determine significance. So We'll have example 4, which is testing the significance of R. Okay. And that is suppose, suppose for, suppose for the hours studied, suppose for the hours studied and test scores, we have the Pearson correlation coefficient to be 0.95. Like we are just assuming this scenario, and we have 10 to be the number of the sample size, and then wish we wish to test the significance of the correlation at alpha equals 0.05. So we know that for step 1, so for step 1, we need to compute T based on the formula given. Compute T, and we know T is R square root of n minus 2 divided by square root of 1 minus R squared. So that is, and here now we have our R is 0.95, n is 10. Based on what we have, R is 0.95, n is 10. Then we have T equals 0.95 square root of 10 minus 2 divided by square root of 1 minus 0.95 all squared. That is approximately 7.40. You can check that up to be sure. And then that leads us to step 2. Step 2. So for step 2, we need to look up the critical value, of T, the critical value of T for n minus 2, which is equal to 10 minus 2, which is equal to 8 degrees of freedom at alpha equals 0.05. So let's take that value to be this. Suppose it is 2.306. Of course, you have to use your own table, check your table and be sure whatever it is. Whatever happens, the decision rule is what matters at the end of the day. So be sure you get the correct thing in your situation. So since T, I like to call this T test, the test statistic, since the T test is 7.40 and it is greater than the T critical, anything you get from the table is the T critical, which is 2.306 in this case. So we have to reject the null hypothesis. You have to reject the null hypothesis and conclude that the correlation between hours studied and test scores is statistically significant. Statistically significant. Okay, so we have come to the end of that. So in this analysis, of course, we covered how to calculate the Pearson correlation coefficient, interpret its value, and determine its statistical significance. Understanding these concepts is actually essential. We need to analyze relationships between variables in various fields, including psychology, finance, research, or whatever field you want to talk about. So with this, we've come to the end of this video. If you have not subscribed to this channel, you want to do that right now. And of course, hit the notification bell so you can always get alerted each time a new video is released. And don't forget to comment, Tell me if you want me to teach a topic or solve a problem, and like also and share so that more people can have access to these things. And watch out for the next video, the next correlation video, which is about the Spearman's rank correlation. Till then, have a great time. Bye.